So let's do it. So the first type of activity I'm going to talk about is solvent activity. And this is for highly non-ideal solutions. So I gave you that example in the previous lecture of my own thesis work, like a concentrated sodium chloride solution would be highly non-ideal. And so what that means is you don't have a predictive way of calculating its properties, such as vapor pressure. So now this is specific for solvent activity. So I'll write lowercase a for activity, and I'm going to just put of species A, so that could be water or ethanol or whatever our solvent is. So I'll say solvent is indicated by this letter right there, whatever the solvent is. And lowercase a for activity. Okay, activity. All right, so for solvent activity, that equals the observed vapor pressure of species A divided by the pure solvent vapor pressure. So this is for, a solution. So really we're kind of saying this is solvent activity, but we recognize that this is the solvent activity of A in a solution. Okay? So this would be the pure vapor pressure of the solvent. And then now this is the measured vapor pressure of the solution. Okay, and so I showed you that example again with the water and the salt. So we know that when you have a solution of sodium chloride compared to that of pure water, so if I write H2O here, but then now I've got a solution that's salty water, so I'll just say NaCl aqueous. Okay, there's vapor pressure here, and there's vapor pressure here. So we'll say this is the pure vapor pressure, right? And so we know that the pure vapor pressure of the water is going to be greater than the vapor pressure when we add solutes. So this is one of our colligative properties. And in fact, I'll make this, I'll change this to observed to be consistent with our activity. So whatever we measure the vapor pressure of this solution to be, we could calculate the activity of that by ratioing it to the vapor pressure of the solvent. And what would be useful in this kind of exercise would be to look at activity versus like perhaps mole fraction. So as we add more solutes, we see, and actually I should write it as, I could write it in terms of activity of the solvent, but I'll write it in terms of the mole fraction of the solute, right? And we know as we add more sodium chloride, the vapor pressure decreases, so we'd see something like that, okay? So generally activity doesn't have to be for vapor pressure, so it's a general measurement. And so let me draw a line here, and so we'll say in general terms, okay, activity is defined as the following. It's the limit of the activity divided by gamma, here, which I'll talk about in a minute. And all of that just equals the mole fraction as this gamma coefficient approaches 1. Okay? So effectively what you're seeing here on this graph, that's kind of what this is showing, right? So on this graph where chi NaCl is 0, and chi NaCl is never going to approach 1. We're never going to have just like pure sodium chloride. We're only going to get to where it's saturated. So maybe I'll say chi NaCl 0.1. But we know on the top of this graph, if I made this chi H2O, where chi NaCl is 0, chi H2O is 1, right? And so what this thing is kind of saying, this limit is, as you get to a more and more dilute solution, your activity approaches 1, so it approaches the pure case. Okay, hopefully that makes sense. So that all equals 1 as you approach that limit. All right. And so now what that means is, generally, activity is the following. The actual activity, so the activity that you would measure, equals the activity coefficient which sometimes that's referred to as fugacity in the case of ideal gases. But I'm not going to spend a lot of time talking about fugacity. If we had more time, I'd spend more time with it. But it's kind of one of these more obscure ideas. Okay? So let's see here. And so, of course, we know as the activity coefficient approaches 1, then the mole fraction will approach 1. So as our activity coefficient tends to the non-ideal value, which is 1, our mole fraction tends to the non-ideal value of 1. Okay? And so we could write this in terms of the chemical potentials. So I could say the chemical potential of the solution equals the chemical potential of the pure liquid plus RT times the natural log of A. Okay, the natural log of the activity. And I'm just going to do some quick algebra here. What we could also do, and this is getting into the statistical mechanics of activity, right? So if I rearrange this equation, so if I subtract these two, so I subtract that to the other side, so I'll say mu A solution minus mu A star. I'm running out of room here, okay? And I'm going to divide by RT. Oh my God, this is terrible. Divide by RT. And now if I take E of both sides, right, then I can see that this is related to that kind of Boltzmann-like formula, right? That the activity is E raised to the difference of the chemical potentials divided by RT, okay? So sorry that that's kind of sloppy there. Okay, so moving along.